Okay. If there's no questions, then we can jump right back into. Oh, yes, go ahead, Aaron.
Homework from Monday, said it was due next Wednesday, is that correct?
Next
I
Wednesday?
think so, it didn't say the day. Sunday, yeah, it wasn't today, is that?
That's a mistake on my part. I thought I'd fixed that. Did I not fix
When
that?
I looked at it
Oh,
yesterday
yeah.
afternoon, it said not.
It says Wednesday, September 2nd.
Oh, space now.
It's fixed now, yeah. So if I messed you up a little bit,
We tried to do it tomorrow, but
yeah, that's fine. I'll try to remember when I get back to the office to change the link, because that was my mistake. To give you a little more time if I did mess you up, but yeah, but it was meant to be due today. Okay, and you will get homework today that's due on Friday. All right. Okay, any other questions? Yes. Probably in 2 weeks, middle of September. Yeah. All righty. And I'll take a look at that probably when we come back from Labor Day. Then we can take a look at it and see, you guys can look at your other schedules, see when you have tests in other classes, and we can find a suitable day. It works for the majority of the class. I know it always makes someone unhappy, but that's how life is. All right. So we were talking about the energy equation. And we got all the way through the energy equation. We identified all the different parts of the energy equation. We identified why the energy equation is different than Bernoulli's equation. And at the end of the energy equation, we had that head loss term. And we broke that head loss term into two parts. The head loss, H sub L, we said that H sub L is equal to the friction loss plus then the minor or local losses. All right. And it's that local loss, we want to start off with the friction loss. Now, based on fluid mechanics, we know that the friction loss can be a function of the friction factor and the Reynolds number. Oops, I did that wrong, didn't I? Yeah. Okay, in our math speak, the friction loss is equal to a function of the friction factor all right, I'm headed down the wrong path here. Let me just gather my thoughts for a second. The head loss is not a function, it is a function of the friction factor, but rather than the friction factor, it's actually supposed to be E over D. Let me back up here. E over D, where E is the roughness, height, and R sub E is the Reynolds number. Okay. Okay. That's the physical properties of our pipe. What is the rough?
What's the D?
Oh, D is diameter.
Oh, it's diameter.
Yeah.
I thought that's what it was.
Yeah, D is diameter. Let's put to make sure that we're all on the same page, so that's good. There's supposed to be a little comma there in between them. So remember back to fluids, dimensional analysis. We went in, we did the Buckingham pi theorem or whatever to come up with pi terms, whatever method you wanted to use. Buckingham pi theorem is just one technique. But we found some pi terms, and those pi terms that we found said then that the head loss is a function of E over D and the Reynolds number. Okay? And now we have to have some correlation between E over D and the Reynolds number. And once again, I don't think Many of you took fluids from me. I know a couple of you did, but let me do a brief historical background there, okay? Way back in the late 1800s, I believe, there was a guy by the name of Nicarossi. Nicarossi had figured out that the amount of head loss or amount of pressure that you need to push water through a pipe is a function of how rough the pipe is. So he took a bunch of pipe, glass pipe, very smooth pipe he could find, which was glass. He then took some glue, wiped the inside of that pipe with glue. He had gradated sand, so he knew what the size of the sand. He'd broken them down into different sizes. And he put then all one size of sand in each pipe, and then he tested those pipes. And what he found was at lower flows with Reynolds numbers less than 2,000 approximately, that everything collapsed onto one curve. And then as the Reynolds number started to ramp up, it broke off into these individual families. Okay. And so he found that this matched the dimensional analysis, that E over D, the roughness of the sand particles. So sometimes you'll hear that called the equivalent sand roughness. That height of that particle and the diameter of the pipe was key in finding the friction factor or finding the head loss for most flows. Now I keep wanting to throw the friction factor in there, but I don't want to go there just yet. All right. Along came a couple of guys, Holbrook and White, and they said, okay, can we take Nicarassi's data? And I have all this stuff in my fluid. I don't have a copy here. But they said, can we take Nicarassi's data and can we find an equation that will fit his data? And they did. They sat down and they came up with an equation to fit his data, but the equation was very complex. And so we'll get to that equation here in just a minute. But it was very hard to solve that equation. So pre-computers, it wasn't very practical. All right. And some other people tried different things, and a lot of different people came up with empirical equations to find what the head loss is in a pipe. Right? Now, little side story to this. I don't think I shared this in here. Well, maybe I'm. Well, let me wait with that story. So because it was so hard to find that relationship between the head loss and this equivalent sand grain roughness, other question? Anyone online that has a question? Okay. 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 So one of these equations that came out was called the Hazen-Williams equation. All right. And the Hazen-Williams equation is a little bit different than what you're used to. Now, I'm going to show you this equation, and it's important that you know how to use it because it's still being used. All right, it's still being used today by especially old timers. And I guess I should say, well, I know when I use it because I'm kind of an old timer, right? Some people just won't let it go, even though the other equation that you probably learned in fluids, the Darcy-Weisbach, which we'll get to, is more technically sound and it's more accurate. Well, some people have learned the Hazen-Williams and this is what they know, and it works pretty good. It works pretty good. And so they just go. There is a guy that owns, I think, 20 electrical power plants. He has built probably another 20 on top of that. Ted Sorensen Engineering up in Iowa Falls. Very good at what he does, and had an opportunity to interact with Ted Sorensen just a few weeks ago. And he talked about that, in this discussion that continued on because he said that large diameter pipes fail to follow the equations. And it's true. And like I said, I'll put that story off for just a little bit, but you know, I was real surprised that he still uses the Hayes and Williams equation. But it works for him. And he's obviously been very successful at it. So that's what I want to cover right now is the Hayes and Williams equation. So this is the equation that's been used for a lot of years. I wish it would just die. But you need to be familiar with it because you'll see it in reports. You will see it in studies. The Hayes and Williams equation then tells us that the velocity is equal to phi times c of hw times r sub h raised to the 0.63 times then the slope raised to 0.54. Okay, let's define each of these terms. Phi is a conversion parameter where it's equal to 1.318 in the English system, or I'm sorry, not one. I got mixed up with the Manning's equation. 0.849 in the SI system. Okay, so depending upon the system that you're working on is going to depend upon which value you use for phi. C sub HW is the Hayes and Williams coefficient. Okay, and the Hayes and Williams coefficient is based on the pipe type. All right. So plastic pipe's going to be different than steel pipe. It's going to be different than wood. If you've ever seen wood pipe. And so obviously if we need the Hayes and Williams equation, we're going to go to our book and we're going to pull these values out. Let's see, is that in chapter 12? That actually may be in chapter 12. I don't use it, so I don't even remember where it's at.
It's 404 in the third edition book.
404? That's a weird, they must have changed quite a bit. I still haven't got my book. I'm still waiting for it. Okay, and what chapter is that in the third edition there? 470 here. So it is chapter 12. All right, here we go. So 12.1.1. So you can see here that for the type of pipe that we have, smooth glass or plastic, cement mortar line trowel, we have a Hayes and Williams C right here. And these values range from 90 up to about 150. All right. We also have a Manning's N, and for those who've taken engineering hydrology, you're familiar with Manning's. And then we also have Moody diagram. This is the relative roughness right here, E or epsilon. It's also called epsilon. And we'll come back to that here in just a minute. But so if you are dealing with some cast iron pipe or some wrought iron pipe, so commercial steel wrought iron right there would say Hayes and Williams of 140, all right? This is why it's been so popular, is because it makes a lot more sense, not sense, that's not the right word. it's a lot easier for people to identify with a value of 140 rather than a friction factor of 0.017. And they look at that and they say, that's pretty small. I just can't compute that. But I get 90, I get 120, I get 140. That makes more sense. And so people have liked it, but it's also an explicit equation, so it falls right out. So even though it has these weird coefficient or these weird exponentials right there, even with a slide rule, this equation was easier to solve. So let's finish classifying the rest of this equation. R sub h, that is the hydraulic radius. Okay, and the hydraulic radius is equal to what? Anyone remember what that's equal to? Good. Area over wetted perimeter. So A represents the area, P represents the wetted perimeter. Wetted perimeter then is the perimeter that is wet. Imagine that, right? So if I have a full pipe flow, the entire circumference is wet. So for circular pipes, what does the wetted perimeter, what does the hydraulic radius collapse to? All right. Anyone have that? Good to go? Okay. So if we had full pipe flow, and we look at that, so the area over the wetted perimeter, area is pi over r squared. We'll kind of go back to the traditional area there rather than pi over 4 divided by d squared. And the perimeter is 2 pi r, right? That's the circumference of the pipe. So if it's full pipe flow, the wetted perimeter is going to be the entire circumference. So now we can simplify this. That cancels out, pi cancels out, and we're left with r divided by 2 or d divided by 4. So a lot of times when we say wetted perimeter of, the hydraulic radius of the pipe, and we know it's full pipe flow, we just throw in d divided by 4 and move on. Okay. All right, so we've defined every term here now but S. So what is S? Well, S then is the slope of the hydraulic grade line or the HGL. Now you've seen that, right, in fluids? May not quite remember what it is, and we'll come back to that point as well, but the hydraulic grade line is how fast the piezometric head, the pressure and elevation, is changing in our system. So S represents that slope, okay? Now, if I have a pipeline and I'm trying to find the head loss across my pipeline, how do I do that? Come back to this equation, it's like head loss is not in that equation. If I'm trying to find how much pressure I lose from point A to point B in my pipeline, it's not there. It's not explicitly in the equation. So that's where you need to understand the concept of what S is. S then becomes the head loss per length. Okay. So if I want to find the head loss in my system, I now stick that in there for S, and I can solve over the given length of pipe that I have, I can solve for the head loss in my system. Now remember, head loss has two parts, friction and minor losses, local losses. They're all wrapped up into that head loss term. But what happens if I want to find the velocity in my pipe and I know the head loss? So let's look at a simple example or a concept. Okay, if I have one tank supplying a smaller tank. And if I do this really simply, my hydraulic grade line, not worried so much about minor losses on this right now, but my hydraulic grade line essentially shows that that is the loss right there. That's the hydraulic grade line. So how much head have I lost in my system? Well, I initially had as much head was in the tank 1. And when I get over to tank 2, that right there, that distance right there between those lines represents then my head loss. Because I have certain potential energy in tank 1 and a certain potential energy in tank 2. And I've lost that by the time the flow gets to 2. Okay? But if I want to find the flow rate, and I know the head loss, so if I knew that this was 100 feet and I knew that this was, say, 60 feet, so I've got a head loss of 40 feet and I have a length of pipe of, say, 2,000 feet, I can now plug that into my equation. Let's come back to the equation here. Okay. Plug that into my equation. I now know the slope, head loss over the length. I know the hydraulic radius, d over 4. I can look up the Hazen-Williams coefficient based on the type of pipe. My correction or my conversion coefficient here based on the system I'm using, I can find the velocity. Okay. But what happens if I don't know the actual head loss, but I kind of know the velocity of my pipe? But now I've got a bunch of local losses. So, okay, now how? I know head loss is a function of friction loss and local losses. How do local losses come into play here? Well, what we have to do with the Hazen-Williams equation is we have to use equivalent lengths. Okay? So, in the Hazen-Williams equation, all right, we compute local losses or minor losses using equivalent lengths. Okay. For example, one elbow could equal 10 feet of pipe. So I have a pipeline that's 1,000 feet long, and I have 5 elbows in that pipe. Well, now inside of my equation, I would say it is 1,050 feet, because that additional length of pipe would account for the losses in my in my things like elbows, which are a minor loss, right, Aaron?
Is there a table that would say what those elbows are or what the?
Yes. So there's 2 ways of calculating it. Okay. 2 ways to find. All right. One is look up. Second one is compute using minor loss equation. So the best source for looking up this is the Crane manual. Crane number 410 manual. All right? Crane Company makes a lot of valves and so forth, and so they've done a lot of work. Well, I mean, it's pretty old data, but it's still good. So we go back and we look at what do they compute, and they've got tables and charts based on the radius versus the diameter, the pipe type, and everything. The second way to do it is to go back to the minor loss equation. All right. So the minor loss equation, we're going to incorporate that when we go back to calculate using the Darcy-Weisbach with the energy equation. But let me show you what it is, because I know you've seen it from fluids. All right. The minor loss equation right here is that the minor loss is equal to some coefficient K times B squared over 2G. Seen that in fluids, right? Okay. So where the minor loss coefficient, so K is the minor loss coefficient. That is from a book as well. So if I jump back, chapter 4, then we've got a bunch of tables right here. And we just look in here, like table 4.3.1, pipe fitting, 90-degree elbow, regular, somewhere in this range here. K is equal to 0.21 or 0.3. And we go all the way down here. We have valves, butterfly valves. These are, I think we talked about these briefly, valves to open and close, a plate inside of the pipe that rotates. Well, that's based on how open it is. So we've got different minor loss coefficients there. We've got expansions and contractions on table 4.3.2. And we can look at these here and say, all right, if we have a contraction and we have a relationship of D2 over D1, the upstream and the downstream, we can come down here and we can find, based on the angle of how fast it contracts, we can find different minor loss coefficients. This is just a sampling, just like anything else, just like the equivalent lengths. The Crane manual is really good. You go online, the internet has a bunch of information. Once again, this is just a simple sampling of those minor loss coefficients. Okay. So if we know how much minor loss, what is the head loss due to the minor loss, then we can go back and we can correlate that to a pipe length. And that pipe length then we can use inside of the Hazen-Williams equation. All right. May not be clear just yet, but hopefully as we continue to go over this, will come clear to you. Okay. All right. Yes.
Are we going to be using the Hazen-Williams equation in like a test, or is that just?
Yes. Yes. As much as I wish it would die and go away, I really do.
Will help us let it die by not making it through. None of us will ever do it, we're engineers.
Well, you may have to. You may have to do it if you're reading a report and they say, you know, this is, you're reading through the equations like, where did this come from? And you want to validate the numbers or whatever, you may have to actually know how to use it. And it, once again, it's pretty, it's easy. It is, it's plug and chug. Grab the value, stick it in, crank it out. Okay. Now, the one thing we haven't covered yet with the Hazen-Williams is we've talked about the velocity being calculated right there. But oftentimes we don't care so much about the velocity, we want to know more about the flow rate. So what's the correlation between the flow rate and the velocity? There you go, okay. So bottom line, then we get to the flow, and Q is equal to V times A. So if I stick A inside of that equation, anywhere, doesn't matter, right? If I just stick A over here, now I can change that to Q. And that is probably more used than this one because we often want to know flow rate more than we want to know the velocity in the pipe. Okay. Okay. Let's work one example with Hayes and Williams. And then we'll come back to it again after we talk about friction. Okay. So Hayes and Williams example one. We have a single pipe between reservoirs. All right. It's galvanized iron. And has a length of 2,500 feet and a diameter equal to 8 inches. Okay. And the head loss across the system, or the, let's do it this way, the reservoirs, the delta Z across the reservoirs is equal to 35 feet. And what we want to find now is the flow rate. So we go ahead and we open up our book again. We come back here to galvanized iron pipe. Galvanized iron pipe. Hayes and Williams then is, I don't know if you guys can see that. 135, can you see that? Okay, from here I can't see it. But, so just want to make sure. Okay, so that's 135. Okay. So I know that the solution phi is going to be 1.318 because I'm going to be working in the English system. C sub HW is 135. All right. My diameter, I'm going to put that into units of feet because this is an empirical equation. So 0.667 feet. Probably went too far, just call it 0.67. All right. And we already know the length up there. So now we just go ahead and put it in into our equation that tells us that Q is equal to phi times C of HW times the area times the hydraulic radius to the 0.63 times the slope. And since I don't have the slope, I have the head loss over the length, bless you. I have 35 feet over a length of 2,500 feet raised to the 0.54. Okay. So if you're like, what? I'm not sure I understand this picture. You know, a reservoir and a tank is kind of the same thing. So we can kind of say that we have a tank here and it's flowing down to this other tank or reservoir down here. Okay. This is 2,500 feet of 8-inch pipe. And the difference between these two is 35 feet. So from here, it's plug and chug. So Q is equal to 1.318 times 135 times the area, which is going to be pi divided by 4, times 0.67 squared, times the hydraulic radius, which is going to be 0.67 divided by 4, diameter divided by 4, raised to 0.63, times then 35 divided by 2500, raised to the 0.54. And there we have our equation, and all we have to do is crank it out. And we'll go ahead and crank that out. We get then Q is equal to, right, this comes out really nice, 2 cubic feet per second. Okay. Any questions on that?
Where does the 4 come from?
The 4 comes from the fact that we have to find the hydraulic radius. And the hydraulic radius we determined was equal to the area over the wetted perimeter, which we then determined, if we simplify it for full pipe flow, is D divided by 4. Yeah. Aaron?
So if we have a question on a test, you would give us the tables, get that information.
Correct. I wouldn't expect you to memorize the Hayes-Williams coefficients. Although that would be kind of
So we
fun.
would have to memorize the Hayes-Williams equation.
I don't know. I have to decide on that.
Depends on how nice we are.
No, depends on how nice I am. Okay.
Will you put your examples back?
Oh, sorry. Yes, be happy to. Lauren?
I was just looking.
Okay. So now let's get back to equivalent lengths. All right. Once again, you can look it up, or you can go to, or you can calculate it. So I want to talk about the Darcy-Weisbach equation really fast. Darcy-Weisbach equation tells us that the friction loss is equal to the friction factor times L over D times V squared over 2G. Let's put that in parentheses. Okay. Remember the minor loss coefficient? Minor loss we said was H sub minor is equal to K times V squared over 2G. So it's pretty simple, actually. So equivalent lengths if I have a one-dimensional velocity, if I have 8 feet per second going through my pipe, what's going to be the one-dimensional velocity going through the elbow? 8 feet per second, right? Conservation of mass, has to be. So look at this. If my velocity head is the same, okay, I can now equate F over L over D is equal to K. So if I'm trying to find equivalent lengths for my Hayes-Williams equation, and I know it's a pipe elbow, I go to the chart, I look up K, got it. I know the diameter of my pipe, got it. And based on the pipe type, I have a friction factor. The only known now is length. So that right there, I can go ahead and calculate my equivalent length of my pipe by just simply solving that right there. The equivalent length in the equation is equal to K times D divided by F.
If you have a change of pipe diameters where velocity changes, can you break that down into smaller incremental sections?
Yes, or you can account for that based on different different diameters. Well, you can actually, okay, So different smaller sections.
Right, where you have a decrease in the diameter of the pipe, the velocity increases because of the decreased cross section. In order to preserve Q, in order for Q to be equal, when the pipe gets smaller, velocity goes up. But if you
Right.
looked at all of the equal velocity sections and broke them up into smaller chunks, can you still do this? So like this undetermined length of pipe has a certain velocity and a certain diameter, and we do all of the calculations for it. So this section of pipe, which may in reality only be 60 feet, it might have a length with all this calculation of like 62.5. Can you like break the pipe up into chunks if there's changes of velocity over the length of the pipe?
Yes, yes, yes. You
Okay.
break it up, or you treat each diameter different as you move through the pipe, because the minor loss coefficient, I mean, if you change the diameter, the velocity over here and the minor loss also changes, right? As it does for over here. So you just need to account for the new diameter to account what is the equivalent length in the 10-inch rather than the 8-inch. So if I understand the statement, yes, you're breaking it up into parts and solving it for each part, and then adding all those equivalent lengths back up for your system. And that is the correct way of doing that. Okay. All right. We've got 6 minutes here, so let's do another example. Well, I'll tell you what. I'm going to do it like this. Can you read that okay? Those online? It's okay, yeah. So you're analyzing an old system. So in your notes, old system, check calculations. So we have a commercial steel pipe that's 800 feet long, 5 elbows, the diameter is 4 inches. We're gonna neglect entrance and exit losses. We'll get to those when we get back to Darcy Williams. I'm sorry, Darcy Weisbach. And the flow rate is 70 cubic feet per second. So what we're trying to find, in essence, is we know the flow rate we want to push through this pipe. And we want to know if we have, say, 30 pounds per square inch at the entrance of the pipe, what are we going to have at the end? So we're trying now to find the total head loss. So now we know the flow rate, we're trying to find the head loss now. Okay. So since we're going to use Hayes and Williams, we have to find the equivalent length of the culvert, and then we have to calculate the head loss in the system. All right. So for the solution, just kind of went there and calculated a few things. I got my diameter in terms of feet, my length, my flow rate, my so for right now, don't worry about this E and E over D. All right, just say, okay, we're going to assume a friction factor of 0.0195. So you should remember how to find the friction factor from fluids, but just, we'll cover that again. Just jump down and say, okay, this is the friction factor we're gonna have, all right? So all this is information, which is, you can compute, it's given to you. Now, I'm gonna go ahead and go to the book and say, all right, it's a 90-degree regular elbow. And so K is equal to 0.26. K, remember, was between 0.21 and 0.3. Throw this back up here again. Okay, so 90-degree elbow right there. So in absence of any other information, well, let me move this over. Absence of any other information, I'm just going to split the difference. So I selected 0.026 for my minor loss coefficient. Okay. And I have that equation right there right now. So now that I know my diameter, I know K, I know my friction factor, which came from the Moody diagram. Once again, don't be too worried about that just yet. If you don't remember how, just assume that friction factor. So now I can find L of 4.4. That's the key right there. Any questions up to that point? Aaron?
So that's just for each elbow.
That's for each elbow, correct. Okay. Now remember, I'm going to change for each minor loss, I'm going to add length to my pipe. So my pipe has an actual length of 800 feet, but I have 5 elbows. So I'm going to go ahead then and calculate the new length of my pipe that includes the minor losses. So 800 plus 5 times 4.4 is going to give me then 822 feet of pipeline. I should have put units here.
What that is like total length of the pipe plus the elbow?
It's not the actual length of the pipe plus the elbows, but if we actually took the elbows out, but wanted to maintain the same head loss that those elbows create, I would replace that elbow with a piece of pipe that's 4.4 feet long, and I would make it straight. And then I would have the same loss in that straight pipeline as I would in the pipeline that's got the curves in it, the bends in it. Okay. So now that I have that, if I go and find my Hayes and Williams coefficient of 140 for commercial steel pipe, pull that out of the table. So C sub HW is 140. Now I can just go ahead and plug and chug into my equation, put everything into my equation, and I'll find that my head loss is 44.9 feet, or basically 45 feet of the system. Okay,
So
well,
is the equivalent like the 4.44 or the 822.2?
so there's each elbow has an equivalent length of 4.4 feet,
Okay.
but I have 5 elbows, so I have to multiply it by 5 because 5 elbows in my system to give me a total equivalent length of 822. Any questions about that? Okay, we're past time, so I appreciate your patience. With that, I will upload homework for you today on the Hayes and Williams equations. And Friday, and we will see you on Friday. So have a great day.
Will you, what was the answer?
The answer to the first one,
The first example that you did?
it was 2 cubic feet per second.
2?
Yes. Mhm. Sure. Okay.
I'll see you in the meeting tomorrow.
Tomorrow? Okay, wonderful.
1 to 2?
What's that?
1 to 2?
Is that what it is? I honestly can't remember.
I think
So-
so.
Okay, wonderful. Yeah, we'll see you tomorrow then.
Bye.
Okay.